Okay, everyone's here. Let's get started. So yesterday, we're dealing with systems of particles now. And again, this is very general. Solid, gas, liquid, or combinations of the two. And we proved, towards the end, we proved Newton's second law for a system. This is called Newton's second law for a system of particles. And it has the form of Newton's second law for a single particle, F equals ma. But you have to pay attention to what this F is. This is the net force, of course, and it's just going to be the external force. The internal forces cancel in pairs by Newton's third law. So they're not going to survive in here. This is the total mass of the system, and this is the acceleration of the center of mass. So the way we think about this is, the system, no matter what's going on in the system, the center of mass you can imagine all of the mass to be concentrated at the center of mass, and all of the forces, external forces, to be concentrated at that point. And that's, Newton's second law describes how that point moves. I didn't say that really well. So it holds for the center of mass motion if we imagine, so we're imagining the entire mass of the system to be concentrated here, all the forces to be concentrated here. And then you can just write down Newton's second law, and it turns out to be correct. That's what we showed. F equals ma. But again, you want to respect this. This is the total mass, and that's the acceleration of the center of mass. So I guess the usual way to say, the usual way to say this is slightly different. Is this the center of mass moves as if all the mass were concentrated there and all the force were concentrated there. I think that's maybe a slightly better way of doing it. And we did a demonstration. Remember the mallet thrown in the air? The center of mass of the mallet goes in a parabola. Because if you imagine everything concentrated at the center of mass, and you throw something in a uniform gravitational field, you get projectile motion, right? It's a parabola. So, what about the Earth-Moon system? Remember the Earth-Moon, the center of mass?
Inside the Earth.
The Earth wobbles a little bit, in other words, okay? So when the Moon is going around the Earth, like this, the Earth is moving a little because it's the center of mass. In that frame of reference, it's the center of mass that's going to remain motionless. So the Earth wobbles a little bit, right? What about the Sun?
It theoretically should.
It's going to wobble too, mainly due to Jupiter. In fact, this is one of the ways that people have discovered that there are planets, outside of our solar system. They look at the light coming from stars, and if the star has a little bit of wobble, right, due to this planet, one or more planets going around here, when the star is coming toward us, if it happens to be doing that, the frequency of light emission is a little greater. That's a Doppler shift effect. You guys are familiar with the Doppler shift effect? Right. When it's going away, the shift is, wavelengths are shifted, the frequency's a little less, okay? And this can be measured very sensitively. And so that's one way that planets, the existence of so-called exoplanets, as people do that.
Aliens.
What?
The aliens.
Yeah. The ancient aliens, yeah, the people who visited us long ago. And
that's how Einstein got all his theories.
yeah, right, anyway, yeah.
So I got help there.
And Bill Nye.
Okay, so this is interesting. This is a real simple apparatus, okay? And you remember the center of mass lies here, right? So, as a demonstration of Newton's second law for a system of particles, I'm going to go to the center here, the geometrical center, and rotate this thing, rotate it around. So, it's supposed to be uniform circular motion. It damps out quickly. Why is it damping out so quickly? Well, where's the center of mass? It's over here, right? What's the center of mass doing? It's going in a circle. There's got to be a centripetal force. What's supplying that centripetal force? Me, I've got to hold this thing here. That's one thing. I've got to hold it as rigidly as I can. But that force is ultimately going to come. There's a normal force here. When this thing is rotating, there's going to have to be there's an increased normal force here, and that increases the friction. So because we have acceleration of the center of mass here, we've got to have a force. And that force is going to come from this rod, and there's going to be an equal and opposite force here on the support, and that's going to cause friction. What if I rotate it at the center of mass? What's the acceleration of the center of mass?
Zero.
Zero. And we don't require any force, right? Very different. Look at that. Right? So now the frictional force is much reduced. We don't have that needed normal force here to cause that center of mass to move, to accelerate. Any questions about that? Here's another interesting demonstration. So this is a inclined ramp. Okay, it's got this wedge shape here. So I'm going to set it on the table here, and you can see that it's going to slope downward. Right? Can everybody see this? So to show you that it's sloped downward, I'm going to put this rod on here, and you can see it goes down the incline. Okay, so this is down the incline. Everybody see that? Okay, what about this? It goes up.
Science.
What? I couldn't hear.
Science.
Yeah, it is science.
Mystery spot.
If you want to see stuff like this, go see the mystery spot in Santa Cruz. Now, a lot of that stuff is optical illusions, but some of it is genuine. This is genuine physics. It's not an optical illusion, okay? And I need to reword how I said it here. This is not an optical illusion. This is really happening. We have to explain this. We can't go on with our lives without explaining this. Okay? So, but the mystery spot does have some genuine physics stuff, but a lot of it is sort of these optical illusions and things too. Okay, so let's see. I release this from rest, right? It gains kinetic energy. And because it's going up the ramp, it gains potential energy. Ooh, patent time. This appears to violate energy conservation. So, does anybody know what's going on here? You can actually, yeah, the center of mass has to be going down. There's no question about it. Because the potential energy has to be going down so that the kinetic energy goes up. There's no question. Our problem is to understand how the center of mass is going down. And I just noticed here, you can actually see. So here is what we think of as going up. But can you see what's happening here? Because of the wedge shape and because of the conical shape here, the center of mass is going down. It is going, oh, I guess, well, you can't, I don't know if you can see this, but yeah, or you can look at it this way. The center of mass is going down. So this is a great demonstration. Yeah?
So now let's say if the angle was increased to the point where it was
This angle of inclination here?
and yeah, if that was increased to the point where it would still go down the other way, would that go overdo the tendency to?
Yeah, right. Oh, yeah, right. In fact, what I thought you were going to say is, if this is inclined just the right amount, and I put this on here, it'll just stay there. Yeah, right.
So there's that critical point there.
Yes, exactly right. That's the right word, critical. Okay, so here's a sphere, right? What's going to happen if I put the sphere on here?
Roll down.
Well, first of all, this has kind of a big radius. If it has a larger and larger radius, it's going to start to look like this. You know, if I have a very large radius here, it's going to be essentially flat here, and so it should roll down there. Okay. On the other hand, you know, if I imagine this to be smaller and smaller, it looks like, you know, it should go the other way. So what happens with a sphere is this. I'm going to start it right here, okay? So now it's approximately flat. It should behave like a rod, and it does. I didn't give it a, you know, I let that go from rest, right? But over here, it goes the opposite way. It only took me about 15 years to make the leap, you know. Did this, everyone does this demonstration, and they don't tell you about this one. It's the secret. It's a secret. Okay, any questions about that? Here's an example, sort of a standard example here. We're going to assume that we have this projectile. It's fired from the ground here. Some initial velocity, some angle. It's not going to really be important. And we're going to look at the special case of where right at the top, right at the apex here, there's an explosion. And it explodes into two equally massive, this is a very special case, okay, to start off with. It explodes into two equally massive parts. One of them is projected horizontally, and the other one is instantaneously at rest after the explosion. So it's going to fall from rest straight down. Now you might wonder, is this possible? Yeah, if you think about it, it's possible. You can imagine there's a spring. You start off with these two masses together, and there's a spring between them. It's compressed. This thing goes up here, and right at the top, the spring is compressed just the right amount that it's going to stop this one dead in its tracks and send this one out that way. Okay, so it is possible. It's a very special case. And we want to ask the question, where does this land? See, it looks like it could be a hard problem, right? But if you think of the center of mass motion, what does the center of mass motion have to be? It has to be a parabola. The center of mass moves as if all the mass were concentrated there. And the explosion is irrelevant. Those are internal forces. You know, when there's an explosion, there's in these two pieces, this exerts a force on this way, and then exerts a force on that way. You can think of the spring, same thing. So the center of mass has to continue this parabola right here, be symmetric. Well, we know what this range is. We have this, remember the range formula way back long ago? We derived? Remember, it's maximized when theta naught's 45 degrees. So we have these two particles here right after the explosion. This is at rest. This one's horizontally projected. They have the same initial height, the same initial y velocity. They both have no y velocity. We did a demonstration of this. Which one's going to hit the ground first? Same time, right? So all along the path, at every point here, they're going to be at the same height, and the center of mass has to be halfway between because they're equally massive. So in the end, when this hits here and this hits some distance over here, this distance has to be that distance because the center of mass is halfway between these two. So the answer is, x is, you can see that it's 1, 2, it's 3 times r over 2. It's 3 halves r. It's got to be 3 halves r. So that's a highly particular case, but it exhibits, you know, how this it can be used. Knowing the path of the center of mass can be useful. What if it was a totally arbitrary explosion, any number of fragments going in any directions? What's the path of the center of mass? Yeah, it's got to be the same. Yeah, no matter how complicated it is. And incidentally, you know, this would occur in 3 dimensions. There's going to be stuff going not just in the plane here, but out this way too. Now, of course, not just any explosion is possible. I can't have this come up here and then all of the fragments go that way. That's obviously not going to be right. And you know it can't be right because then the center of mass would have to go over there, but it can't. It has to go in this parabola in the plane here, in this plane. So there are constraints, and we'll talk more, but we'll see how we deal with that. That's part of this chapter. We deal with collisions. Incidentally, to a physicist, this is a collision. Okay, most people think of a collision as things colliding together, but this is the opposite. So it's like the time reverse situation. So we define collisions to be very general, and a big important part of this chapter is dealing with collisions. That's where we're headed. There's one thing I want to say here that's Oh, so maybe I should just follow the notes. That's why they're here. Is mechanical energy conserved in this collision? In this when there's an explosion? You know, there's a release of chemical energy. I mean, suppose you have a bomb just at rest and it explodes. What's the mechanical energy before the explosion? Zero. Let's assume, you know, we'll define gravitational potential energy to be zero. Okay. After the explosion, we have all this kinetic energy. Mechanical energy is not conserved. Okay. So chemical energy is, if it's a typical chemical type bomb, the total energy is conserved, but you have to include the chemical energy. So, do you think kinetic energy is conserved here, or do you think? Or let's focus our attention just before and just after the collision. So we don't have to. Gravitational potential energy is not important here. Just before the collision, we have this mass moving at some velocity, right? And just after, we have, it splits into two, and we have that, right? Now, the initial kinetic energy is 1/2 mv squared. And I'm going to call, some of you are still having trouble with this. I'm going to call the final, I'm going to call this, it's up to us what's initial and final, right? So you can think of this being the initial state and these two things hitting simultaneously being the final state. Well, that's not convenient now. Right now we're going to just before and just after the explosion. So, what's the, it's not obvious. But we know that this has to be greater than that, because there's been an explosion. It's released energy. So the interesting thing here is seeing why. So how do we show that? Well, what is the velocity? The fact that we know the range here. You'll see that if there was an explosion, it would go along here and have a certain range. This piece has twice the range, so it has to have twice the velocity because it has twice the range. And now what happens when I plug, we find our final kinetic energy. I have 1/2, what's the mass? m/2, and I have, this is amazing, I have twice the velocity. Can everybody see that? And what happens when you do that? You get twice this. Right. There's a lot of twos here. Okay? Keep the 1/2. I see 4 divided by 2. I see that. Here, does everybody agree with this? Okay, yeah. Where did that energy come from? The explosion. Good. There's a simpler way of looking at this we'll see later in the lecture. Okay, there's one more. The center of mass has a lot of properties, and we've just seen one of them, Newton's second law. F equals ma applies to a system of particles, but A has to be referred to the acceleration of the center of mass. There's another property that's very useful in solving problems. Suppose we have an arbitrary system of particles in a uniform gravitational field. What's the potential energy? So it looks like I have to add up all those individual, the total potential energies, the sum of the individual potential energies. So each one's going to contribute, each little particle is going to contribute its mass, g, and the height, y. All right? Now, g is a constant. I can move it through the sum. And what is this? What is the sum of all the individual mass moments here? Remember, it's related to the center of mass. Right. So, y center of mass is just this. So, the sum of the moments here will be the total mass times the y center mass. So we get this very simple expression. And how do we think of that expression? You have an arbitrary system. It's going to have a center of mass. If you imagine concentrating all the mass at the center of mass, and then find the potential energy, that's correct. That's really useful. You don't have to go in and do this. You know, this is what you would normally have to do to calculate it. But it happens to be correct here, that you can imagine all the mass to be concentrated at the center of mass and just find that potential energy, and that's the right answer. So we'll make use of that. Any questions?
Do you have to do that drawing thing like you did yesterday to find the center of mass? Like you cut that blob up yesterday and you found the center of mass. Do you have to know what the center of mass is to do this?
All we need to know is the y value of this. The potential energy is only going to depend upon the y coordinate of the center of mass. So we would have to know that. Yeah. Right. Oftentimes, though, we know it by symmetry, or it's, you know, it's. So you will see examples of the use of this. Okay, so you've all heard of momentum. That's what we're going to get into next. We haven't really, it may have come up, but we haven't dealt with it, we haven't defined it. And it turns out to be a useful quantity. Newton was the one who recognized the importance of it, and he called it the quantity of motion. It's too many syllables, but for us nowadays, but it kind of conveys some kind of importance here, doesn't it? And we will see that it's very important, particularly in collisions, as we will see. So what we want to do here is just set the basic equations. Remember that Newton's second law for let's first consider just a single particle. And Newton's second law is the net force on it is its mass times its acceleration, right? We know that. Well, the momentum being the mass times the velocity, if I differentiate this with respect to time, I just get the mass times the acceleration. So what that means is we can rewrite Newton's second law as the net force on a particle is its rate of change of momentum. That's equivalent. Now this is relevant for what we're going to talk about next. Now we're going to jump to any system of particles. The total momentum is going to be the sum of all the individual momentums, and each of those is mi vi, right? But look at this. Does this look, this is the, what is this? We know that you can replace this with RC, and we know that the vector to the center of mass is given by this, where these are the vectors to individual particles. So I can replace this sum right here with simply the total mass times the vector to the center of mass. And when I do that, I can do this. And when I do that in here, look what we get for the total momentum of a system of particles. So how do we think of this? How do we remember this result? By now, the danger here is that you can come up with relationships for the center of mass that seem really obvious, and they're not true. Okay, so that's what I do at higher level mechanics when I test students. Okay, it's one of them, but we're not going to do it here. But look at this. The total momentum, which is the sum of all the individual momentums, is identical to what? How do we say this in words? Imagine all the mass to be concentrated at the center of mass, find and multiply it by the velocity of the center of mass, and you've got the total momentum. Nice, simple result. Now there's one more relationship. Before I summarize these, there's one more that we're going to look at. And that relates to the analogy to this. This is for a single particle. There's an analogy of that for a system. And there's different ways of getting at it. One of them is differentiate this with respect to time. Okay? We're going to get dp dt, where p here is the total momentum, capital P, right? Not lowercase p, capital P. The mass is constant, so I get the acceleration of the center of mass. But we know, we just proved yesterday that and we saw demonstrations on it, the force is the mass times the acceleration. We just showed that the mass times the acceleration of center mass is dp dt. So we have this relationship. Now all this, I know this all seems kind of confusing, but this table will help. There is a very strong correspondence here between Newton's second law for a single particle and a system of particles. So here's what we've been dealing with until very recently for this course, right? The corresponding relationship for a system of particles, any system of particles, is the net force is the total mass times the acceleration of the center of mass. We've seen that. This is a definition of momentum for a particle. And there's this, the corresponding relationship holds for the center of mass. The total momentum of any system is the total mass times the velocity of the center of mass. We just proved that. And finally, we have this different way of stating Newton's second law for a particle. The net force is dp dt. We just showed that this applies to a system too. It's the net force, and you just got to use the total momentum here. So these are useful relationships, as we will see. But I admit that they take, seems a little confusing, but there is this, what makes these easy to remember is that they are just straight correspondences from here, right? You just generalize to a system. And when you generalize, this becomes the total mass, that becomes the acceleration as it applies to the center of mass. Similarly here, and this P becomes the total momentum. Okay, so now finally we're going to get deeper. We've already actually talked about collisions, but we're going to get deeper into them now. And that's where we're going to spend the rest of the chapter doing this. So the fact that there's a collision can mean different things. One of the important aspects of any collision is that it lasts a relatively brief time. So what do I mean by that? Well, maybe this diagram here will help. Let's say we have two particles coming in and they interact. They could be billiard balls bouncing off each other, any kind of a situation. But the key idea when we talk about collisions is, here they're not interacting. Okay? There's going to be some well-defined or maybe not so well-defined region where the interaction starts to happen. And then on the other side, after that's happened, now they're separated, and the interaction is negligible. So there's some fairly well, to some extent, defined region here where there's interaction. So we have an initial state where there's no interaction. So in the absence of any external forces, this is just going to move with a constant velocity. This moves with a constant velocity. And then they interact and they go off like this. Now in this case, M1 has come in here, it's gone out here, and M2 has gone out there. This is not the only situation that we're going to be considering. For example, one possibility is they could stick together and form a single mass. So you have two masses coming in and a single one going out. Okay? So there's a lot of possibilities here. And of course, you can have, one of these could split up. You could have three particles coming out. So this is the two-particle case where it's two in, two out, and the particles have remained the same here. Their masses are the same. Question? Okay, so to quantify this, there's going to be some interaction force here to make this interesting. And let's call that force F. This is a force that one object exerts on the other, and it's going to obey Newton's third law. So this is the force of 1 on 2, or 2 on 1, doesn't really matter. It only occurs during the collision. And let's suppose that the collision occurs from some time t0 to some final time. Here's Newton's second law, which holds for we're focusing our attention on one of the bodies here. Let's say M1, okay? This is Newton's second law. We can write this in differential form like this. Okay, so this holds over a little tiny time interval. And now we can integrate this over the collision. Over the collision. Remember, f is going to be a function of time. When we integrate it over the collision, we get this integral, which we can't do unless we know what this force is. Typically, these forces, it's a complicated dependence, as I'll show you in a moment. But we do this because we can then, we have a relationship here. This quantity is called the impulse. I don't know if you guys have ever heard of this before. At this level of mechanics, we're not going to use it too much. In fact, it never gets used all that much in calculations, but it's convenient for developing the theory. There are problems when you, really the only way to do them is to use impulse, but I don't know if we're going to encounter any of them here. They're typically a little higher, intermediate level. But we're going to introduce it here because it's useful. We call this something. You know, we don't know what it is, so we call it something. It makes us feel better, right? Because you need to know the details of this force, which, like I said, is typically complicated. But what this is on the left side here, this is we call the impulse. This is the change in momentum, the final momentum minus the initial momentum of, let's say, 1. This has some final momentum, has some initial momentum. It's changed due to the impulse of the other particle on it. So we can write that the change in momentum on a particle is equal to the impulse on that particle. That's that boxed relationship. Now, we have some collisions occurring here over some time. It starts at some time, ends at some time. Typically, it could look something like this. All right, that's probably very hard to calculate that, but it doesn't really matter because we can gain a lot of physics information without dealing with the details here. So one of the things we can do is we can define, well, this will come up. So now for this to make sense, we really want to think in terms of one dimension here, because this force could be, in general, three-dimensional. But we're going to look now, focus on the case of one-dimensional collision. So the change in momentum of the particle is going to be the impulse, which is the integral of f with respect to time. What's the geometrical meaning? If I integrate f with respect to time, what's the geometrical significance or meaning of that? Area under the curve, right? So there's going to be a constant force, the average force here, that has the same area. That's how we define the average here. It's very natural. So there's going to be a value of the force somewhere here. You know, this is too high, this is too low. There's going to be some value such that the area of this rectangle equals the area of that. In that case, the impulse is just the average force times the time. That's going to be this area, which is equal to that area. So we've lost the details of the force, but often in collisions we don't care. Okay, so we can now, the impulse is that average force times that time base there, that's delta t. We can now solve for the average force, all right? And we get this expression. Now, remember here, these deltas they're typically small compared to our experiment. Now, usually, this is relatively small here. But the change in momentum of this particle is not necessarily small, right? You can see that. This has been a significant change in momentum. So you don't want to think of these deltas as small here. Where is it? Okay, so this has a very important application. Suppose, for example, suppose you're in a car and your head it's moving, and your head has, let's say, just focus on the head, has some momentum. And then you hit something, and the momentum of your head goes to 0 for however. right? There's been a change in momentum of your head, right? To minimize damage, you want to minimize the force. So what do you want delta T to be? As big as possible. So this is a very simple idea. You know, this is why they have padded dashboards. This is why boxers wear gloves, or are supposed to wear gloves, right? You're increasing that interaction time. The average, and it's pretty obvious, okay? I mean, I don't know if you, I think we could argue it just qualitatively without showing these equations. But by increasing this time for a given change in momentum, somebody hits somebody, and I mean, there can be damage done to, you know, not just the person's head, but your fist too, right? To minimize the damage, you want to spread out that time as much as possible. So, airbags, same idea, right? All right, let's do a calculation here for a baseball and a bat, just to help this stuff sink in. So we have this pitcher pitches a ball at 30 meters per second. That's pretty fast, but you know, that's. I don't think your kids could probably do that, but you know, adults can do this, right? Major League Baseball players, it can be, fastballs are in the 90s, right? Has anyone gotten over 100? Wow. Yeah, that must be interesting to stand at a plate. Anybody stood at the plate when, oh, they have these pitching machines. They still have those? So has anyone actually stood at a plate and with a ball moving at 100 miles an hour and try to, I don't know if I should ask you if you try to hit it. Can you just stand there and not, you know, it's like the faith in physics thing. Has anyone ever done that before? Been subject to a pitch at 100 miles per hour? I wonder what it's like.
It's quite fast.
Yeah, well, yeah. I mean, you know, you blink and, you know, where's the ball? And it's yeah, right. That's another question. Right. Wow. So the catcher would want to.
That's why he
the ball has a good. That's right. Right. Usually an extra pad is going in there. Right? You want to spread that collision time out. Whoops. Okay. So let's find the average force, typical average force on a ball due to a baseball bat. So we're going to assume this incoming speed. The bat, we're going to assume typically the collision time here is roughly milliseconds. That's typical. And let's say it goes out at 50 miles an hour. So what's the change in momentum? Well, it's the mass. The momentum is the mass times the velocity. But you want to be careful here. This is the final momentum, which is positive. What's the initial momentum? It's negative. So if I have something come in at a certain momentum, and let's say it goes out at the same momentum. Forget this right now. Something comes in a certain momentum, and it goes out with the same magnitude. What's the change in momentum? No, it's not zero. It's twice. Because you have to take the final minus the initial. So you can see it right here. We got two minus signs. So if something comes in with momentum like this, it goes out with momentum like this. When you take the difference of those two, it's going to be twice. This is a common mistake. That's why I'm bringing it up. This one's a little bit more complicated. It doesn't have the same speed, but the idea is the same. You don't take the difference here. I mean, you take the difference, but one of them's negative. So you're ending up adding the magnitudes of the momentum. So we get this, kilogram meters per second. The average force is the change in momentum over the change in time, and it's 8,000 newtons. So this is the weight of roughly 800 kilograms. So a newton, right, a kilogram weighs about 10 newtons. So, and 800 kilograms is huge, right? But I do want to point out, it's only lasting for a short time. 1.5 milliseconds, right? But it is a very large force by our standards, daily sort of standards. Okay. So the next thing here is this, and here's where we're going to utilize our relationships here. Often in collisions, there's no net external force, okay? And even when there is a net external force, if you look just before the collision and just after the collision, that net external force is not going to really affect anything. This is kind of a fine point. It's called the impulse approximation. I don't know if we're going to see that. We'll find out when we do the problems. But anyway, it's often true that when there's a collision, the system is isolated. So what does that mean? Well, here's our Newton's second, one form of Newton's second law for a system of particles. If the net force is 0, what do we have? P is constant, the momentum is conserved. So now we have our second conservation theorem here, that when you have no net force on a system, the total momentum is a constant of the motion. That's called momentum conservation. Now that doesn't mean that the momentum of each particle in the system is, momentum can be exchanged, but the total momentum has to be the same, very much like energy. There is one difference that I want to point out, however, and you want to be careful about this. This is a vector. So in 3 dimensions, there's actually momentum in the x directions conserved, y and z. Energy is just one relationship. So what's happening here is this. When objects come in and have some kind of collision, there's going to be a change in momentum of this one due to the impulse exerted by this particle. The impulses are equal and opposite because the forces are equal and opposite by Newton's third law. So the changes in momentum are equal and opposite. So these things come in, this one changes by a certain amount of momentum, this is going to have to change in equal and opposite momentum. So the total momentum is constant. This kind of seems out of place, but and so I'm going to think about trying to find a place, a home for it. Let me make a note of that. But I just want to point something out here. When we have no net force, when the total momentum is constant, when there's no net force, the total momentum is conserved, it's constant. This means that the velocity of the center of mass has to be constant. Because remember, the total momentum is the mass times the velocity of the center of mass. And the mass is constant, so the center of mass, regardless of what happens in any kind of explosion, the center of mass in an isolated system has to move with constant velocity. So as an example, let's go back and look at our previous, remember remember this? We can actually look at this from a little different, a simpler point of view here. We're going to again focus on right at the top. Maybe I should bring this back up here. So we're going to look, well, here it is. We're going to consider this just before and just after the collision. Gravity is not, the collision takes place over such a small time. Gravity won't have had a chance to really do anything to the system. So it's over a little bit of time interval right here at the top, there's where the collision occurs. We don't have to worry about gravity. So momentum will be conserved just before and just after. So we start off, do I still have the, yeah, here it is. So we have this, we have the explosion and what happens, it occurs precisely such that this one is momentarily at rest. So what does the velocity of this one have to be? Momentum has to be conserved, right? The momentum is the mass times the velocity. Now the momentum is just in that. What does that velocity have to be? It's got to be twice the velocity, right? Because the product of the mass and the velocity. This mass times that velocity has to be this mass times that. This is there's an initial momentum mv here. There's a final momentum just after the collision. It's m over 2. That's got to be 2v. That's easy. We had to think a little bit more about that earlier. But this is just a different way of looking, a momentum way of looking at it. We get the same result. Okay, so here we're going to do some problems, and here's a demonstration. Okay, now this is an air track. Remember an air track? The little holes, air comes out, the gliders float. The air's off, so there's a static friction. They're not moving. All right, and you can see I've made this kind of leaf spring here that's under tension. When I turn on the air, these things are going to move in opposite directions because the leaf spring is under tension. It's going to push them out. All right. So what's the initial momentum?
Zero.
Thank you. What's the final momentum? The total final momentum? It's got to be zero. There's no net force here. There's a gravitational force, but there's a normal force. This is an isolated system, effectively. This happens to be half the mass of this, and I even had to tune it a little bit here with some weights. This is half the mass of that. So what's got to be true if the total momentum is zero? I got half, it's similar to that, I got half the mass. This has to have twice the velocity. So it will cover twice the distance that this one covers. All right, so I've arranged this so that this is 60 centimeters. From here to the bumper is 60 centimeters, and this is 30 centimeters. So what should happen when I turn on the air?
Same time.
They should hit at the same time. Now, don't expect something real dramatic. This is very sensitive to the level here, and I think there's weird things going on in this when the spring comes up here. But anyway, I'm going to do it on 1, 2, 3. That was roughly the same, right?
It came pretty close to the first starting point, you know?
Pardon me?
When they hit the bumpers and came back, they came almost exactly to where they
Oh,
started.
okay, yeah, I've never noticed that. Yeah, this is, yeah, thank you. So anyway, that's, and I've always had trouble with this demonstration, and I've worried that when the leaf spring expands here, it's kind of torque, it can maybe cause an edge to dig in a little. The friction could be different. There could be some friction here that's different between these two because they're different masses and different shapes. I suspect something like that's going on here because you don't know how much time I spent doing this stupid little demo, and it's just. You can very carefully level the track. It's just, I think there's something else going on there. But anyway, it's roughly right. Here's a quantitative example. So you have, we did a demo similar to this with the moving platforms. So you have two people and one pushes on the other. It doesn't matter who does the pushing, right? And they're initially at rest. They're ice skaters. And let's say we know that this one goes 3 meters, is after the collision here, when they separate. This person's moving 3 meters per second. What's the velocity this one have to be? And here are their masses. Well, the momentum has to be conserved. The initial momentum is 0. There's no friction here, or negligible friction. The final momentum has to be 0. So I've got this right here is one equation and one unknown. I know everything except V2, and I can solve for it, and I get this. Okay, and I've been careful with the signs here. Often people just they know that they have to be going like this, so they don't worry about the signs. But it's up to you, however you want to handle it. But this person, now wait a minute, why is this person moving less speed than this person? Heavier, right? And the greater the difference here, the ratio, the greater the ratio is going to be. Now, we can make another step here. You notice how we needed to have information on this. What if we didn't know this? Could we solve the problem? Could we find their final speeds? No, and because we don't have we don't know how hard they pushed, right? And that's hard to quantify. But look at this system. So that's how physicists think. A spring. Springs are our friend. Okay, so we imagine. So we're going to take these two masses. Let's take them to be 2 and 3 kilograms. We compress the spring, and we tie it. We somehow clamp it and put a string there, and we burn the string, or however you want to do it. We have initially no momentum, and then we have this release of energy, and we're going to have final momentum. So now momentum has to be conserved, but something else is conserved here too. What is it? Mechanical energy, right? So here's the conservation of momentum. We did this just before. Now we know the mechanical energy is conserved. The initial mechanical energy is all in the spring, 1/2 kx squared. And incidentally, we're given how much the spring is compressed here. And that must be the final energy is all kinetic. The spring's in its relaxed state. So what we can do is, so we have two unknowns here. We have two equations and two unknowns. We don't know V1 and V2. And we can solve them. With a little bit of effort, we can solve them. Let's just leave it. Let's don't spend any more time on it. And we'll do examples in class, in problem session. Okay, any questions about that?